Professor Sara Seager. She's a professor of physics, planetary science, and aeronautics and astronomics. Astronautics at the Massachusetts Institute of Technology, where she holds the class of 1941 professor chair. Her groundbreaking research ranges from the foundation of exoplanet atmospheres to innovative theories about life on other worlds to development of novel space mission concepts. And she was the deputy science director of the national mission TESS, PI of the JPL-MIT CubeSat ASTERIA, and has had numerous leadership roles in concept development for space-based direct imaging missions to discover another Earth. She currently leads the Morningstar missions to Venus to search for signs of life or life itself in the Venus clouds. We're so pleased to have her here. And thank you, Franco, for seeing her at NEAF and dragging her out here. Please welcome Professor Sara Seager. Oh, yeah, we gotta change the screen. How about that? It's a red, all the way around. One more time. There we go. Hello.
Hi, everyone. Can you hear me?
Yes.
I'm not sure if you can see me over there, but you can see my talk, right?
Yes.
Okay. Well, I will just take it away. I'm here to tell you about something new. I call my talk From Lab to Cosmos, 3 Frontiers in the Search for Signs of Life Beyond Earth. Now, as most of you, you all know this, that our Earth's atmosphere is filled with oxygen to 20% by volume. But without life and without plants and photosynthetic bacteria, we would basically have no oxygen. So we consider oxygen a sign of life because oxygen is so reactive that without it being continually produced, there just wouldn't be any in the atmosphere. So what's really, really amazing, striking actually, is that nearly 100 years ago, an astronomer, James Jeans, in 1930, he had a textbook. And in the textbook, it seems like he's the first one to have kind of written this down, that we know that oxygen is continually being discharged into our atmosphere. And because it's so reactive, it shouldn't be here. And therefore, oxygen might be a good sign of life on another planet. And Jeans, later down on the same textbook, he reports that he looked at Venus with his telescope. I don't know what kind, but he didn't see oxygen. And instead, he put an upper limit. So that's how we want to find signs of life elsewhere. We want to find, one idea is to find gases that don't belong, that can, maybe in the context with their atmosphere, help us understand that there might be life there. That's a really hard thing to do. And I'll very, very briefly talk about how we're thinking about gases that might be signs of life on other planets. Mostly, I'm going to focus on Venus. And Venus, by the way, does have a tiny bit of oxygen, way lower than Jeans could measure himself. I'll talk about some space missions to Venus, and then I have a brand new topic for you. So, Earth, oxygen's a great gas as a sign of life, but our Earth has only had oxygen in its atmosphere for less than 1/4 of its life. So if we want to think about all those Earths that might be out there, wow, well, for most of their life, they might not be showing oxygen. So it really behooves us to try to think of what other gases might there be? Not just oxygen, but what range of gases might there be? And the James Webb Space Telescope, our current best telescope for searching for signs of life, or trying to search for signs of life, it doesn't encompass visible wavelengths where oxygen is strong anyway. Well, I just wanted you to know there's literally thousands and thousands of gases out there. There's just so many gases, untold numbers. We have done some combinatorics, scraped all the literature, literally came up with all the possible molecules that could be gases at room temperature and pressure. We made algorithms, we sorted through tons of them. And we found out of all this, this is a bit of an aside, but I just want to tell you, I've thought a lot about this problem. We've done a lot of due diligence. And you know what my favorite biosignature gas is? Actually, it's not oxygen. It's a gas called phosphine. Now, I wonder how many of you have heard of phosphine. It's not really a gas we hear much about. It's very, very rare. On Earth, no, although the element P is a major biochemical element for life, we don't really hear much about phosphine gas because on Earth, phosphorus, P, it matches up with oxygen to make compounds called phosphates. We have very little hydrogen floating around on Earth. We have the wrong temperatures and pressures for phosphine to exist in an energetically favorable way. So phosphine caught my attention through this framework or just in general. And that would be my favorite biosignatures gas for exoplanets of the future. But what happened was someone across the globe, Professor Jane Greaves, was also intrigued by phosphine, and she wanted to try to find signs of life on our sister planet Venus. Now I'm thinking, because you're all staying up with astronomy, you may have heard of phosphine on Venus. And this came out in the fall of 2020. So basically, Professor Jane Greaves invited my team to join her team because we had been thinking about phosphine and reading about it and writing papers. And she had found a tiny signal of phosphine on Venus. And she invited us to join her team to help with interpretation and to help to propose to get more and better data. So this talk is not about phosphine. I'm just trying to warm up to more about Venus, but we made this announcement. We didn't say there's life on Venus, okay? So if you were there or you were reading, that's not the announcement. We just said, wow, we have a tiny, tiny signal of phosphine gas in the Venus atmosphere, in the cloud layers. We have worked through all known chemistry, and we don't find any chemistry that could make phosphine, even in the tiny levels we've detected. And wow, how do you think this was received? Well, it wasn't received well, let's just say. So basically what happened was looking back, we can kind of summarize everything into 3 questions. Is the signal real? You know, people are debating that. It's a tiny signal in very noisy data. If the signal's real, is the molecule correctly identified? Could it be phosphine or could it be something else? That is being debated. But even if those first 2 are correct, the signal's real, the molecule's correctly identified, well, it's very hard to associate it with life. Very, very hard. Because, hey, even though 100 pages of known chemistry doesn't explain the presence of phosphine, there could be unknown chemistry. So I just wanted you to know where this stands. But that definitely leads me into talking about Venus. And this was just supposed to be an introduction. There's lots and lots of gases that could qualify as biosignature gases. It's really challenging to assess gases as a sign of life for the reasons I just mentioned, that they're probably tiny signals. It's a really, really hard thing to know from far away whether a gas has some unknown chemistry or known chemistry, or whether it could be associated with life. So we're going to move on to Venus now. And the thing about Venus is it is so hot at the surface due to a massive carbon dioxide greenhouse atmosphere. It's so hot. It is 700 degrees Kelvin. We would not survive on the surface. No life that we know of or could conceive of could survive on the surface of Venus. But just like here on Earth, if you hike up a mountain, you know, or go in an airplane, it gets colder and colder. And so too on Venus. So about 50 kilometers above the surface, it's the right temperature for life. And there are clouds on Venus. They're vertically extensive. They're always there, not like our fragmented clouds. And so on our Earth, we have some life in our clouds, bacteria that get swept up and stays there temporarily. So it kind of sounds like a good idea. And as far as we know, it was Carl Sagan who first proposed the idea that there might be life in the clouds of Venus, or that there could be. Well, one thing they didn't know at the time was the clouds are not made of water. They're made of concentrated sulfuric acid. And that's nasty. I don't know if you've ever got to use it. Probably not, because it's so dangerous. It'll burn a hole right through your clothes and skin, and it destroys all of our life. Here's just a schematic of Venus showing you the 0 where the surface is. It's just a cartoon showing you where the clouds are. But I just want you to know they're made of one of the most dangerous compounds we could ever imagine. Our life could never survive there. And just to put that point home, I'm going to show you a classic demonstration. I'm not going to do it for real. If I was more organized, I literally could have set this up in my lab, but I'm going to show you a demo, a video demo. So, our life is made of DNA. And our DNA has a sugar molecule. You may remember like the sugar phosphate backbone. So we're going to use sugar as a proxy for DNA, which is a proxy for life. So this is sugar in the glass container, just like sugar you would get from your house or from a store, just table sugar. And this is concentrated sulfuric acid. This is me with like these really serious acid protective gloves. On the right, you'll just see a cartoon. It's to remind us that sugar is a proxy for DNA, is a proxy for life. So this video is supposed to help you understand why our life could never survive. It's sped up to 2.5 times. On one side, you're seeing the infrared through an infrared camera. And look what's happening. The sugar and sulfuric acid are reacting. It turned color. It's hot. Look at it on the right. That doesn't look good for life if sugar is a proxy for life. Watch what's going to happen. Wow. That is hot. That is steam. That is water vapor and sulfur dioxide coming off of the sugar. And that nasty black mess is dehydrated carbon. When we show, look at that, it's just incredible. Every time I see this, it's like, wow, I just can't get over how crazy this is. We don't let visitors touch it or look at it, but one visitor, after it was all over, wanted to smell it. And before we could kind of say, no, it's probably not a good idea, smelled it. I smelled it too. It smells like cotton candy. Yeah, so that's why, I mean, who can blame people for being against the idea of life on Venus, right? Like, surely we would all agree there could never be life on Venus based on that video. But that's not our attitude, right? We're explorers. We want to see what's out there. And so what my team did was we started to do laboratory experiments. Our DNA can't survive, but for example, we took parts of our DNA. We took our nucleic acid bases, so the latter part, ACGT, and we put those in concentrated sulfuric acid, and those are stable. They are stable for like 1 year or more, like as long as we bothered to measure them. There's some chemical reactions, not like reactions going on, but they're just for any chemists in the room, they're getting protonated. Protons are coming off of the sulfuric acid and they're getting attached to the nitrogen atoms. So that's pretty exciting. And what our goal is, oh, by the way, you can just look at this until I'm ready to tell you about it. We put our amino acids in concentrated sulfuric acid, our 20 biogenic amino acids. And you know what? With one exception, they're all stable. Some are chemically modified, but the rest are stable. And our initial goal, or our current goal, is to generate a DNA-like molecule. So not our DNA, but swapping out parts. Swapping out unstable parts for stable parts, because we want to convince ourselves, you, our sponsors, that it's worth going to Venus to search for signs of life. Not because of phosphine, but because complex organic molecules can survive in concentrated sulfuric acid. And I'm really pleased to tell you we have a milestone result where we have showed not DNA, but a kind of cousin molecule that's only human made called PNA, peptide nucleic acid. It is stable. A single strand of it is stable in room temperature in concentrated sulfuric acid. There's so much here I don't have time to tell you about. I will just mention one thing very briefly. I know I could just only talk about chemistry. I don't know if there's an amateur chemistry society, but astrobiology, it's just phenomenal. What you're seeing here is we put lipids, these like fats with a polar head, into concentrated sulfuric acid. And when you do it in water, they will point their polar heads outward and they will make like a little tiny spherical vesicle. In astrobiology, people are trying to make life from scratch in the lab. And this is one of the steps, like towards a very, very primitive cell membrane. Well, what these pictures are, they're microscope images of putting these in concentrated sulfuric acid. They not only are stable, but they form these little miniature spherical vesicles. So in any event, you just need to know that, wow, there are so many things going on. It's too complicated to explain all of them. But to summarize this first frontier, frontier number one in the search for signs of life beyond Earth, it's not about phosphine. It's about our sister planet Venus, where the clouds have the right temperature for life. They're made of liquid concentrated sulfuric acid, and there's energy from our sun. So that's not new. We knew about all of that. What is new is that biomolecular building blocks like amino acids and nucleic acid bases and like a whole list of others, they are stable in concentrated sulfuric acid, shown by my team's like repeatable high signal to noise laboratory experiments. And that's totally amazing. It's astonishing because there could be life there just made out of slightly different building blocks. So, what are we going to do all about all that? We want to go to Venus. And the search for signs of life, it's still crazy. Like I could show you, I could take you on a lab tour and like tell you all about the chemistry, but it's still people can't quite move their minds over to this idea. And we don't have community support to go to Venus to search for signs of life. It's just not a thing. So I'm pleased to have started my own consortium to do this. And I'm going to update you on that in a moment. But right now, I just want to remind everyone, if you're not already aware, that there are missions on the books to go to Venus. And one of them is Da Vinci, NASA's Da Vinci, which is super exciting because it'll drop a big probe down through the atmosphere. And this probe will measure gases and a lot of other things. It won't be investigating the clouds, though. And we have not sent a probe down through Venus's atmosphere for over 4 decades. While back in the 70s and early 80s, the former Soviet Union and NASA the former Soviet Union sent over a dozen probes that went down through the atmosphere. So the Europeans have a mission plan called Veritas. NASA has an orbiter called Envision. And other countries have plans too to go to Venus. But I'm here to tell you about this series of missions called the Morningstar Missions to Venus. So you probably, let's see. Oh, was anyone awake really early today and saw the crescent moon? It was unbelievably beautiful. It was like the thinnest crescent, like it was so spectacular. Probably tomorrow's new moon, but it was beautiful. And I haven't seen Venus for a while, but I know like at least a few weeks ago, I was seeing it shine brightly in the morning sky. That's why we call ourselves Morning Star Missions to Venus. But we're also trying to capture, like we want to help a new dawn rise. That instead of waiting 4 decades to go to Venus's atmosphere or another planet, we could have some small focused missions go more often. So we have an idea to send a series of missions to Venus focused on finding signs of life or life itself. And these missions would be like small short-term mission, medium in complexity and kind of longer term, and maybe extreme in complexity and very long-term mission. So I'm going to tell you about the first 2 missions. And the first mission, we call it the Rocket Lab mission to Venus. We're working with Rocket Lab, a company that has launched over 70 successful small rockets, on the smaller side of rockets. We're working with Rocket Lab, and I'm going to update you on where this mission is. On the top left, you can see our probe. Remember, small mission, low complexity. This is the real probe and the real size. So it's like about this big. It's going to weigh probably about 25 kilograms. It's not going to open and it doesn't have a parachute. It's going to go down through the atmosphere and slow down based on its own drag. And we were allocated 1 kilogram. So this is the probe. It's got its heat shield put on by NASA Ames, and this picture is taken at NASA Ames to protect it as it enters the Venus atmosphere, to protect the probe from burning up. And we have a single instrument. This is a photograph of the instrument on the right here, where we have our instrument. It's going to shine a laser through an opening, laser port over here. I guess, wait, can you see I don't know if you can see my cursor there.
Yeah, we see it.
Oh, you can, okay. So it's going to shine, you can't really see the hole, it's kind of hidden by this shadow. It'll shine a laser out through this unit, and it will focus 20 centimeters outside of the probe. We're trying to avoid the airflow around the probe in case it does dislodge some particles and in case they vaporize, and we don't want to interact with those. We want to interact with the Venus clouds. It'll shine this light and it'll come back into this collecting lens. And once it comes in here, it does a few different things. It scatters off this mirror and will go back down to the bottom to a detector. And it also goes this way into this beam splitter and goes to two separate channels. It's going to do essentially two separate things. We're looking for fluorescence, like autofluorescence, like if you remember like a kid's funhouse or a nightclub when it's dark but your white clothes and such light up. We're looking for fluorescence because it will tell us that the particles in the Venus atmosphere are not pure concentrated sulfuric acid, that they may contain organic molecules. So it doesn't mean there's life there, but all life needs organic molecules, and it's what we're searching for. We're also going to measure the backscattered polarized radiation. And nothing in nature scatters equally in all directions. If you went around with a laser and shined it at like raindrops or dust particles or anything, trust me, nothing will scatter that light equally in all directions. You know that at least for water, because you've all seen a rainbow where light is both bunched up and spread out at the same time. And encoded in that scattering is information on the particle. And if it's a sphere, there's information contained on its composition by its index of refraction and also particle size distribution. So we're going back there. We're going to confirm some old things and learn some new things. But this is a first largely privately funded mission to Venus. Our target launch date is 2026. You can see the probe is ready. The instruments are ready. We still have a ways to go. I'll skip the bottom right and move to the left. Part of our extended team, Professor Chris Carr from Georgia Tech, has tested our flight spare on this light aircraft, like it's a drone, and flown it in Hawaii on the outskirts of the volcanic fog, both to test the entire systems engineering, like does it all work? Does it talk to itself and us like it's supposed to? And it was kind of hard to squeeze it into this, by the way, because when we get put into the probe, Rocket Lab, the company, will have supplied everything we need, like the power and the radio and everything else. But we had to disperse it all those pieces into this drone to make it like the mass equally distributed. So that's where we're at with this mission. We have a lot of lab data. We're really working hard to get this job done. The next mission we want to send to Venus, we've been having like a kind of back and forth about what this mission should be. But we'd love to send a parachute mission to Venus to last half an hour or 1 hour in the clouds. And we have a new idea where we want to have miniature molecular sensors. So what you're seeing in the middle here is like a parachute that would be about 5 meters in diameter. And on the bottom would be a little probe. And that probe is shown here. Let's just look at the bottom left. There'd be a pressure vessel with an antenna. And this big giant thing on the bottom, this kind of surrounding material, we're calling this an aerofairing. And what we'd really like to do is have these little tiny patches filled with miniature molecular sensors. And these miniature molecular sensors would be designed to target specific classes of organic molecules. Like the amino acids or the nucleic acid bases are way more complicated molecules even. We're trying to find like a series of complex organic molecules as potentially a sign of life on Venus. And I have some examples on the right. I picked this one example for you. It's called a carbon nanotube. And these carbon nanotubes are super tiny and they're highly electrically conductive. And what researchers do is they call it a defect, but they add a molecule to it. And this added molecule is specially designed so it can target a specific molecule. And when it matches its target molecule, it's like puzzle pieces joining together. And it changes when molecules join together, it changes the electron configuration, hence it changes the electrical conductivity. So essentially what you do is you're measuring resistance. And when this thing interacts with the particle it's designed to interact with, it changes the resistance. Obviously, there's way more to it than what I said, but I just wanted you to know there's a whole bunch of these different kinds of miniature molecular sensors we're exploring to put on these patches because we want to find very specific organic molecules to know whether the ingredients for life are there or whether we can argue that there's life in the clouds of Venus. So while we don't have those sensors now, to build something for space, there's at least 100 steps. And I wanted the team to take steps this summer before we have our miniature molecular sensors chosen and locked down. So we did get to try it out. We tried on the top left, we tried these sensors. These are temperature, pressure, humidity sensors. And an undergrad student put all this together, put it in this printed box. And like, here's his battery. He's got a little microcontroller here. Here's a couple other sensors. And this box went in, I'm going to let you try to figure out where this is going. This box went inside this styrofoam cooler. There's a GoPro camera here. And this is Claire, my master's student at MIT in Aeroastro. She designed and constructed a parachute. And this is a ribbon parachute, so it doesn't self-shred. And we put all of this together onto a weather balloon. Now, I didn't know until this summer, because I know you're an amateur astronomy society, but I don't know if you know, there are also amateur weather balloon societies. And they, just like you, are really helpful, right? You have outreach and you bring new people in. And I'm sure if someone called you out of the blue to help, you'd be on it. And they were on it.
There goes.
There was also a summer camp there when we were launching. This is right in town. We just launched, like right half an hour outside of Boston, where I'm trying to just get this sound to stop. Okay, so this is a balloon filled with hydrogen. They filled it for us, and the balloon is going to expand to match the pressure on the outside, and eventually it's going to pop. You want it to pop. And we went up to 70,000 feet above Earth's surface. And this is a picture with our GoPro camera. It was a little too high because our camera froze and failed right before we got to 70,000 feet. And by the way, another GoPro camera got too hot because it was one of those 90-degree days. And as we were waiting in the parking lot for the, there's like a weather prediction that's constantly being checked to track it's a tracking prediction, weather and tracking. And the app, it tracks like where your balloon is predicted to go, because you don't want to land in a lake, or you preferably want to land on public property so you can go and retrieve your payload. So what you're seeing here on the left that's the weather balloon that's going to pop. That orange is the parachute I showed you, and the box is the cooler with all the sensors. And there's a couple of other things on here. There's a tracker, and the weather balloon folks had a antenna on their car. It's ham radio communicating so they could track the balloon. This is an app which we followed to follow our balloon. And we were really excited for this chase. Our balloon was almost going to land in a swamp, which would have been bad news because we didn't have a way to downlink data. We were just counting on getting our microcontroller back and attaching it to our computer. Fortunately, it all landed in a tree. That was the good news. Claire's parachute was intact. And wow, you can look in the bottom right here. Our summer student, Eddie Hernandez, his microcontroller was still working. So this was a bit of a foray away from astronomy, more into Venus and engineering. But we want to know if Venus has signs of life. It is right next door. And going to Venus is a big thing. It's a big deal. So Frontier 2, small focused missions to complement the big NASA or ESA missions. These small focus, we were really trying to pull this off. I'm telling you, it could be a game changer if we can get the job done. And honestly, it could be a direction as a nation we need to go with the recent cuts and maybe even looming cuts. We may have to kind of reconceive what we need to get done. So the small focus missions as planetary missions is a frontier. Miniature molecular sensors and getting them rapidly matured and ready for space operation is, I'd say for now, my favorite. Well, I was going to say it's my favorite frontier until we get to my next and final topic. This one's going to be a bit hard for me to pull off on Zoom, especially because I can't see you, you can't see me. So I'm going to have to ask you to bear with me. I'm going to, I haven't talked about this much. So this is like brand new. I'm going to just try to share with you why I'm so excited. But to get to this part of the story, I have to tell you about one more mission concept, and that's sending a balloon to Venus. The former Soviet Union has sent 2 balloons. That's not new. But here's myself and 2 of my team members, Maxim de Jong from Thin Red Line Aerospace and Jared Atkinson, my program director for the missions. And behind us is a half-scale balloon. We'd like to go to Venus with a balloon. We'd like to have time. to float around for a week or two. We want to collect the cloud particles. We'd like to collect the clouds. We'd like to evaporate the cloud material and see what's left over. I'm just trying to impress you with our tech development. But to get to what the frontier is, it was one of the most amazing things we live for. We live for like unexpected. And you can just admire this, those who are into engineering. I'm not going to describe it, but the point is we have plans to go to Venus, capture the clouds, like the way you know how fog will condense on your jacket. We have a special type of fog collector we've been developing. And we'd like to be able to evaporate the excess sulfuric acid, because if there is life, maybe it's very diluted. Like if we went outside and gathered some river water with the kind of tools we could send to Venus, it might not work. We might want to concentrate our sample. And so remember I said there's 100 steps to space. Here's a design, here's a thing. But ultimately, it began with a very simple evaporator. Sulfuric acid has a very high boiling point. So we want to lower the pressure, because if we have to heat sulfuric acid up, it will destroy the compounds we're looking for. So we lower the pressure, add a tiny bit of heat, and we can evaporate the excess sulfuric acid. Okay, so this is just like a first step. So Rachna Agrawal, she's a professor in India now. She set up this pumping system. So it's just a glass container with a pump. And the only special thing about the pump is it needed a special kind of oil that is sulfuric acid resistant in case some sulfuric acid went back into the pump, which it didn't, by the way. Okay, so she gets, there's a little glass plate inside this glass container. Glass is resistant to sulfuric acid. That's why we have so much glass. So she took some material, put it in sulfuric acid, evaporated the sulfuric acid, all good. Then she went and took the amino acids. Remember I told you we'd put amino acids in sulfuric acid. So she had the sulfuric acid, took amino acids, put them in sulfuric acid. It's like a white powder. So you dissolve it. It's like dissolving sugar in your tea or sugar in hot water. Dissolve the powder, evaporate the excess sulfuric acid, and lo and behold, there was the tiniest bit of liquid left over. And she did this over and over again. And unlike with other materials, she couldn't get rid of all of the sulfuric acid. There was always the tiniest little bit left over. So, wow. I mean, I'm really happy. I wasn't around. It was my team. I'm really happy that she did not throw this out or just assume her entire system failed. Like no matter what she did, she couldn't get rid of this. And we didn't know what it was for a while, but we eventually figured it out. And we will say now that Rachna rediscovered. So she didn't discover this on her own. It's already known, but she rediscovered a type of material called an ionic liquid. These ionic liquids, they're absolutely incredible. They get ionically bonded together so tight. It's like just for analogy, like no tighter than super glue. The molecules, just for any chemists in the room, so acid wants to donate a proton, and the sulfuric acid gives away protons, and the proton gets joined to a nitrogen atom. So the amino acid becomes positively charged, the sulfuric acid becomes negatively charged, and they bond together. So it's like your table salt, but it's liquid and so tightly bound. It's insane. You can see a picture of some of them here. Like, look how viscous it is, right? It's wow. I mean, it's just kind of so slow moving liquid. And what's so cool about these is that they're salts. They're liquid below 100 degrees Celsius, held together by ionic bonds. There's thousands in the industry. They're very low vapor pressure. This essentially means we could take our ionic liquid to outer space, and for a while anyway, it would not evaporate even in outer space. And indeed, if any of you are space mission enthusiasts, people have used ionic liquids, not this one, but they've used ionic liquids as fuel, like as electrospray propulsion, because it doesn't evaporate and you don't have to be too careful with sealing your fuel tank. Why are we so excited about these? Well, there's a lot of exoplanets out there that we know of that are too warm for water. They can't have water, or their atmospheres are too low of a pressure. So we're so excited about this ionic liquid because it's the first one people have cast that can be made out of planetary materials, sulfuric acid and nitrogen-containing organic molecules. So out there somewhere, there could be planets that we thought couldn't host life, but that have little bits like puddles of these ionic liquids. And there could be life in them. And that's a way extrapolation, by the way. I'm not saying there is life. I'm just saying that if we take this idea that all life needs liquid of some kind, there can be liquid on planets where water can't exist. Well, I'm going to just wrap up in a moment because I want to make sure I have a lot of time for questions. And this is kind of a complicated topic. I want you to have time to ask me more about this. But the bottom line is that it's a liquid that can exist on a planet that's too warm for water or on a near airless world. And these molecules, they're biomolecule friendly. You can put DNA in them. People put enzymes in them. There's other ones of ionic liquids that people have used to experiment with subcutaneous drug delivery. I always like to say, I wouldn't put this one under your skin personally. So to summarize this part of the talk, Frontier 3. Ionic liquids are biomolecule friendly. They basically do not evaporate. So you don't need giant oceans. You can just have little puddles and they'll remain intact. It's a new possibility for habitable exoplanets. There's a lot of cool places on Earth, but trust me, on these exoplanets or on Venus, it is so different from anything on Earth. We really, really have to stretch our imaginations. I hope that in my talk, I've managed to give you a little glimmer of how to, some work at the frontier and how that is really what we need to do if we want to be able to find signs of life. We have to open our minds and consider the impossible. So to summarize, signs of life elsewhere, biosignature gases are a favorite, but challenging. That's why I focus my talk on actually going to Venus to look for complex molecules. I talked about my first frontier was about Venus and the clouds and the sulfuric acid being able to host biomolecules. I touched on a series of missions called the Morningstar missions to Venus. These are very focused missions with a singular goal to find complex organic molecules in the clouds of Venus. At the very end, I told you about a brand new topic, ionic liquids, that are known to exist in industry, but now can be considered a planetary liquid. Thank you so much for your attention today. I'll flash this slide up briefly, and then I'll stop sharing so we can have a round of Q&A. Thank you.
Liquids, who'd have thought? That is crazy. Do we have any questions in here yet? Are you thinking of some stuff? Do you have a question, Franca?
Looking for microbial life on the atmosphere of Venus. Is it going to be microbial life or?
Yes, the question is what kind of life? Yes, good question. We're not thinking there's really going to be complex life there. It'll be microbial life or maybe even something simpler. Like we do not understand the steps how our life originated on Earth. And I'm now like speculating, of course, but perhaps it's even more primitive than a microbe. Perhaps it's like something that Earth had, but that has been lost to time. So we're thinking very simple life forms in the clouds, in the cloud particles.
Who had kind of thought about this, but having balloon animals up in the clouds of Jupiter and Venus, is that, I mean, what large life would be, I think, a very difficult thing to have on Venus, but maybe not.
Well, it's interesting. And you're referring to Carl Sagan. I wish we could, ask him, what was he thinking? Like, was he like, as you may say, throwing darts at the solar system, right? Like, hey, maybe this planet has life. Hey, maybe that planet has life. Well, in the Jupiter atmosphere, we think of Jupiter as being so cold. But actually, just below the atmosphere, it's very hot, too hot for life. And so, although one might imagine, like Carl Sagan, there's life floating around in the clouds of Jupiter, the big, ginormous convective cells would bring it down to where it would just die. So he postulated that maybe they have like a chambered nautilus, you know, that shell, maybe it can control its pressure and maybe it's like a little balloon of helium that can inflate itself. And that was the only way that he could conceive of life being able to survive in the Jupiter atmosphere. So maybe there's something more complicated. But it's pretty tough there, even though there's liquid and there's like, it's hard to imagine there being like a lot of nutrients. And I always say, you know, the pot shouldn't call the kettle black. So it's not fair of me to give you a crazy idea and say that a crazier idea is ruled out.
Great. Alex, do we have any questions online? No questions online. So yeah, please feel free to type them in and Alex will try and answer those. Any more questions from in here? I bet there are. Oh, Bob's got one.
You got Bob?
Yeah, there are millions of organic molecules, and you're only looking for a handful. Will they be able to detect a variety? Each one detect a variety of molecules?
Well, we're hoping to send 10,000 miniature molecular sensors. These sensors are incredibly tiny, like you can't even see them by eye. And people here on Earth, they're trying to do things with these sensors, like detect cancer in blood. So, you know, running a liquid over this thing and you have like a little matrix and you have a lot of them. So we're not just looking for a few, but which ones we're looking for is a very hard question. You know, we have like a list of our favorite 100. And then I'm answering a different question now. So to answer your question, it's not just going to be 4. You could ask yourself that question. Given that you have 10,000 sensors, how do you want to divide them? You don't want to look for 10,000 different molecules because A, you probably don't have that many to conceive of, and B, you need a lot of redundancy. So we're still trying to figure that out, how many and how to make sure we're redundant. So yeah, it's a really tough job, really tough.
Well, I wish I knew more about ionic liquids to ask you more questions about that because it's such a crazy topic.
It's so
I
crazy,
didn't-
yeah.
Yeah, well, I didn't do any research on it before we put you on. I didn't know we were going to be talking about that today, but I did think about this is if you had all the money in the world, if you had all the funding that you could get, what kind of a probe or what would you do? Where would you go? What would you build
Oh my
if you had
God.
just
I'm
unlimited
really glad you
resources?
asked me that. And let me see, I'm in my office so my office is really messy. Okay, so now you're really asking me what I would do. I would do Starshade. I wouldn't go to
Right.
Venus. I would try to find an Earth twin. So now you gave me a chance to talk about Starshade. So I'm going to try to pull this off. This is Starshade. This is a 1% scale model. And Starshade is a giant specially shaped screen. It would formation fly with a telescope and it would block out the starlight so only the planet light enters the telescope. This is really complicated. Someone thought of it in the 1960s. It has been revived and it has kind of died and been revived like many times. Right now it's in a bit of a being shelved stage, but let me tell you a little bit more about Starshade. So it's a giant screen and it's going to work with the space telescope. And it's going to have to be separated by tens of thousands of kilometers. And both the space telescope and Starshade, which will have its own spacecraft, will have to fly really far away from Earth's gravity, like L2 or heliocentric Earth trailing orbit. Now I'm going to show you something else. It's like a test question, and you are going to figure out what it is. It's related to this. This is 1% scale. So the actual Starshade would be 100 times bigger.
Oh yeah.
Let's take a moment and have someone shout out what they think that is.
Well, that's just one of the tips of it. I assume it's just a tip.
Yeah, look how big it is. It's one of the petals. So big, huh?
That is
Like that.
insane. That's full scale, right?
Full scale. That's a full scale petal. So remember, it's going to be attached to, yeah, it's amazing. I would do Starshade. I would send Starshade to space and I would search. What I would do is I would take like the nearest, brightest, say 12 sun-like stars and hammer weight every one and just find the entire planetary system that's present. That's what I would do with unlimited money.
And would you use like a solar sail to get it out there? I mean, because that sort of looks like solar sail-ish.
Okay. Yeah, it kind of looks solar sailish. No, we would just put it on. We would go out like the James Webb and other things. They're going out to L2, the Earth Sun L2, which is like 1 million miles away. It takes a few months to get there.
Anything else?
Okay, I got a question.
Oh yeah, Aaron's got one here. Hold on a second.
So we've looked at this mission before from an optics point of view, but how how are we planning on flying it in formation?
Aaron works
Okay.
at ARCA, by the way, so that's why I
At
had
where?
some ARCA, ARKA.
Okay, great.
It's in Danbury.
Oh, wow, not too far. So basically there's three things. First of all, how are we going to formation fly? Well, we'll know where Starshade is because it will have, we'll know approximately where Starshade is. Starshade would, on its spacecraft, will have like a giant LED bank. And so the telescope can see that LED bank. And so they're going to start lining up. And once they line up, they will know that they are perfectly lined up because the instrument will be designed so that not all the light will be blocked, but like the reddest most light will like leak around the edges. So you'll see like a special pattern once it's lined up. So the Starshade and the telescope have to have a way to communicate with each other. And the team, I'm just sort of trying to remember in real time here, but the team broke it down to like out at L2, there's very little gravity, you're not fighting like a gravity gradient for these things separated. So they worked out what is really the problem here. And the problem they had was sensing, because if you have your light, your laser, your LED, and it's spreading out so much, can you sense that well enough to do the control loop? And they did like a lab demo and proved to themselves that they can do it. Yeah.
Yeah, I mean, one of the questions in here before we go online, how much would this cost? What is the, how do we do it? Why aren't we doing it?
Yeah, good question. Well, we're not doing it because NASA has chosen a different way to solve the same problem, which I am not, a different way to solve the same problem, and that's with a coronagraph. So it's a light blocking device that goes inside the telescope. But why am I in favor of Starshade? Because the coronagraph right now, it's inefficient. Like the Starshade, its power is it's broadband, it's extremely efficient. It blocks out all the starlight. So the starlight does not enter the telescope. The coronagraph, the starlight, and the planet light are mixed. They go into the telescope, they bounce around all the defects, and it's very hard to separate them afterwards. And you lose so much efficiency with the coronagraph. So NASA is doing a really big mission. It's on the books. It's called Habitable Worlds Observatory. But Starshade, it's more efficient, and you could do it on a smaller mission, enormous big thing, even if it takes 20 billion. And so the community voted for this other thing. There's a lot of options. We can have like a small, if you want to build it and you want it to work, I mean, the cheapest it's going to be is probably 2 billion.
Oh, but I don't think those are huge numbers, particularly, what it used to be. I mean, when you're talking about these major projects, 2 billion is not big numbers.
But for 2 billion, the whole community has to be on board. And it's, it would be a better thing like over dinner or like a cup of coffee. It's like hard to unpack like how it all went. But Starshade is so great that I'm keeping it alive, and I have a website called projectStarshade.com, so you can follow our progress. The idea live. We're trying to keep it current. NASA will set the Habitable Observatory, but we'll see where it goes. Frozen. So yeah. Oh, we do have a question here. Someone asked a good question, which I avoided answering. Is it possible to directly detect these ionic liquids on exoplanets? Can they be spectroscopically identified? Probably not, unfortunately. Right now, if they exist in these puddles, they probably cannot be spectroscopically detected right now, unfortunately. We're still trying to work on whether maybe their breakdown products could be detected or whether there's some other consequence of it. We have taken a lot of spectra of these ionic liquids in the lab, and they do have big features in the infrared. But right now, we're probably not detecting them.